Hello everyone, this is Shiva. So in the previous video, I've discussed a basic problem regarding electrostatic repulsion between two charges, right? And this is the next one, right? So what they've given is that 2 point charges are kept in air with separation between them. Force between them is F1, right? This means like when if the space between the charges filled with dielectric constant 4 and force between them is F2 if one third of space between the charges is filled with dielectric constant 9, right? So then the ratio of the forces in the two scenarios, first scenario to second scenario. So yesterday on continuing that I mean, if two charges are kept in vacuum, right, no medium between them, then electrostatic repulsion between the charges is given by, the magnitude is given by k q1 q2 by r square, where k is 1 by 4 pi epsilon naught, and this value in SI is 9 into 10 to the power of 9. So talk a little bit about epsilon naught. It is called absolute permittivity or permittivity of free space, and which that tells us the ability of the medium to let the field lines pass through it, right? The polarization factor or polarization tendency, or how susceptible the material for polarization, right? Okay, so if there is some medium surrounding between the charges other than vacuum, right, then instead of epsilon naught we should place epsilon m, that is permittivity of medium, and the remaining thing same, that is q1 q2 by r square, that is directly proportional to product of charges and inversely proportional to square of the distance between them. So epsilon m, that is permittivity of medium, and we take another quantity, that is relative permittivity, right? Epsilon r is relative permittivity, relative in the sense with respect to another thing, and here with respect to vacuum we take. So permittivity of medium with respect to vacuum, right, that is dielectric constant. So with respect to vacuum, how much the medium allows the field lines pass through it, that factor is called as dielectric constant, right? We see this dielectric constant in many scenarios, in capacitance we see, and also in other things. And by the way, this k and this k is different. This k I've just denoted for 1 by 4 pi epsilon naught, right? This is just a constant here, and this k is dielectric constant. So there are many k's in physics, right? So yeah, so in place of epsilon naught, epsilon m is there if some medium is there. So epsilon m, from here I can write epsilon naught epsilon r, and yeah, epsilon this quantity 1 by 4 pi epsilon naught q1 q2 by r square is already force between the charges when they're placed in vacuum. So that is fc naught divided by epsilon naught. So epsilon r is also dielectric constant k. So force between the charges when they are placed in medium is equals to force between the charges when they are placed in vacuum divided by k. So when you place some medium between the charges, force between the electrostatic force between them reduces by some factor, right? That is k times. So in the problem, this is continuous one, right? That is fully covered, but in the problem it is partially filled dielectric, right? So first half of it is filled, and the next case it is 1/3 of it is filled. So what I'll do is, so if I say the scenario here, right, two charges, some dielectric between them, that is thickness is let's say I've taken t, and dielectric constant of the medium which I introduced, that is k, and the distance between the charges is r. So when I place this dielectric constant here, that is thickness t, right, the remaining distance which is air or vacuum, that is r minus t, and t is actual thickness of the medium. So how am I interpreting this is, if this whatever the force acting between two charges when there is medium here, right? So yeah, so the medium thickness is t, and the distance between the charges is actually r. So the air medium occupies a distance of r minus t, and medium thickness is t, right? So what I'm doing is, so I'm replacing, I mean, whatever the force, if only this were present, that then I took the force, and only vacuum present, then I took the force, and I equated these two, right? Then I got the effective distance between, or effective distance when field travels through both medium and the air, right? So that is r is equals to root epsilon r dash. So here r dash is distance in the medium. That means I equate this. So what I can do is I can replace this medium with air, substituting this effective distance when only when there is no medium present. So that means if this medium is there, so if the field lines go through this much, I can replace this. So the effective distance only when vacuum is present, then that I can take it as r minus t plus root kt or root epsilon or r dash. Here r dash is t, that is medium thickness, right? So the effective distance I can take r minus t plus root k into t. So since now everything is vacuum, since I've replaced this the equivalent of vacuum, the equivalent of this medium I replaced with vacuum, that I took it as this one, right? So that's why I applied 1 by 4 pi epsilon naught q1 q2 by r square. So here t is thickness of the medium, or thickness that is medium that we introduced. And if two mediums or n number of mediums are present, then instead of these thicknesses you can replace the effective distance in vacuum, right? So there is r minus of t1 plus t2, these two thicknesses. This is up to air medium, right? And if we replace this much, root k into t or root epsilon r into t1, that much we have to replace. So root k1 t1 and root k2 t. So this distance plus these two distances whole square, right? I hope you got the idea, right? So so in first case t is r by 2, in the second case t is r by 3, and this is how we can do it. So if I, in this specific problem, if we do, the ratio of the forces we get is 100 over 81, right? Okay, so I hope you got the idea how to do when dielectric medium is introduced, that is force reduces, and if it is partially filled, we take the equivalent, I mean we replace this medium with the vacuum, right? So if we replace this, the effective distance we have to take. So if the force, I mean the field lines travel this much distance, right, the force, we have to replace the effective distance, and this is how we replace the effective distance. Thank you very much. I'll see you in the next model in the same coulombic force series. Thank you.